is Math 139, Section 2.7, Part B. We're going to continue to solve inequalities that have higher order polynomials in them. In example 2, we already have the 0 on one side. So you'll notice I started right out by turning it into the related equation. I just said it's equal to 0 rather than greater than. With 4 terms, I wanted to point out to you that my first option would probably be to try factoring. But notice that when I try to factor by grouping, I don't get a match between the two binomials. And therefore, I'm going to have to say that I can't factor, at least not using this method. When that happens, I'm going to go back up to the original, and I'm going to say, could I use my rational zeros theorem to find some solutions instead? So if I think about P over Q, the possible rational zeros, I know I have to consider both the positive and the negative for all of them. P is going to be a factor of 1, but that's just 1. And Q is also going to be a factor of 1. That's just 1 as well. So my only possible rational zeros are plus and minus 1. Let's check those out and see if one of them works. I'm going to go ahead and put in the original function, or the original polynomial here. X cubed plus 2x squared minus 2x minus 1. And then I'm going to check just using my table. 1 is a 0. Negative 1 is not. Right? We didn't get 0. So x equals 1, based on what the calculator is helping me figure out, is actually a 0 for this function. Now that I know that 1 works, I'm going to go ahead and divide out that solution so that I can find the others. I'm going to go ahead and use synthetic division, but you can also use the long division process here. That's up to you. Let's see, 1, 2, negative 2, negative 1. I bring down the 1 to start. 1 times 1 is 1. Add those and get 3. 3 times 1 is 3. Add those and get 1. And 1 times 1 is 1. Those add up to 0, which of course is my remainder. And if I did really truly have a 0, that should be 0 all the time. So what I end up with here is x squared plus 3x plus 1. And I need to know where that is equal to 0. Since a sum of 3 and a product of 1 is not going to work, I know I can't factor this, and I'm going to use my quadratic formula. I would have negative 3 plus or minus the square root of 3 squared minus 4 times a, which is 1, times c, which is also 1, over 2 times the a, which is 1. Under my radical, I've got 9 minus 4, or 5. And so I do have 2 real-valued solutions. I'm going to go ahead and get decimal approximations, because when I make my little number line to test my solutions, it'll be a lot easier if I've got decimals. So let's see. I would have negative 3 plus the square root of 5 divided by 2, about negative 0.38, or negative 3 minus the square root of 5 divided by 2, negative 2.62. This is the one I got from the plus. This is the one I got from the minus. All right, so let's go ahead now and test our solutions, or at least the number line based on our solutions. My related equation gave me zeros at negative 2.62, negative 0.38, and then this x equals 1. I'm just going to separate those out a little bit. I need to determine, off the graph there, or off the page. I need to determine for each of these four intervals whether my original inequality is true or false. So, I'm going to go ahead and substitute some test values in, since I already have the function in my y equals. I can go straight to the table. Oops. Sorry about that. Let's try that again. There we go. I already have my function in the y equals, and therefore I can go straight over to the table to plug some things in. All right, I'm going to start with negative 3. If I plug negative 3 in, I get a y value of negative 4. Notice that this was supposed to be greater than 0, according to the original inequality, and it's not. So that's false. Maybe I'll test negative 1 in the next interval. Negative 1 actually happens to be in there already. I get a y value of 2. Again, supposed to be greater than 0. And 2 is greater than 0. So my inequality is true in that interval. I'm going to try 0 over here. 0 gives me a y value of negative 1. Again, checking to see if that is greater than 0. It is not. So we would have a false. And finally, I'll try 2 in the last interval. 2 gives me a y value of 11. 11 is greater than 0. So finally, I get true in my last interval. So, the solution to the inequality is true between these two values. And if I want to, I can go back and I can rewrite them using the exact values from negative 3 minus the square root of 5 over 2 to negative 3 plus the square root of 5 over 2. We had that true. And then also, from x equals 1 out to infinity, our inequality was true. So there is my solution, those two intervals, for that inequality. All right, we'll do one more. Number 3, we have this inequality. And again, I'm going to start by multiplying this out. I need to solve the related equation. So I'm going to both multiply it out. We'll make that 2x to the 4th plus x squared. And my related equation would say equals 15. To solve a polynomial equation, usually I want it equal to 0. So I'm going to go ahead and subtract the 15. And I'm looking at an equation of quadratic form here. I've got my first power exactly double the second one in that trinomial. So I can probably factor using the sum and product method. Looking for a sum of 1 and a product of negative 30. Thinking 6 and negative 5 should work there. So 2x to the 4th plus 6x squared minus 5x squared minus 15 equals 0. And now I can factor by grouping. I'll factor out a 2x squared, giving me x squared plus 3, and then a negative 5, also giving me x squared plus 3. And this time I do get the match for the common binomial, so I can factor that out. And my other factor will be 2x squared minus 5. All right, so this says x squared plus 3 equals 0, or 2x squared minus 5 equals 0. On this first one, if x squared is negative 3, the next would be plus or minus I times the square root of 3, which is certainly a solution to the equation, but it doesn't appear on the number line. Right? There's no imaginary numbers on our number line. So although it's truly a solution, it's not one I'm going to use when I create my number line. The second one, I would have 2x squared equals 5. So x squared would be 5 halves. And x would be plus or minus the square root of 5 over the square root of 2. I'll just go ahead and multiply top and bottom by the square root of 2 in order to rationalize the denominator. So I have plus or minus the square root of 10, and on the bottom the square root of 4 is just going to be 2. Now again, those are exact values for the solution to the equation, but if I'm going to use them to test on my number line, I probably need the decimal approximations. So I'm going to go ahead and get those. And it looks like about 1.58, plus or minus. So going to my number line to test, I have a negative 1.58 and a positive 1.58. And that's going to separate my number line into 3 intervals, and I need to test one value in each interval. I haven't put this related equation into the calculator yet, and I'm actually going to go back up and let's see here. I'm going to test this all the way back up here in the original inequality. So I'll go ahead and rewrite that. X squared times 2x squared plus 1 less than 15. All right, so let's test negative 2 first. I'm going to put this left-hand side into my calculator as y1. And then I can go into the table, and my first point that I want to try is negative 2. That gave me a y value of 36. So I would have 36 is less than 15. Definitely false. Okay. Let's try 0 next. 0 gives me a y value of 0 also. So I would have 0 less than 15, which is true. And last, I'm going to try a y of positive 2. That gives me 36 again. And 36 is certainly not less than 15, so I'm back to false. So in this case, the only interval in which my inequality was true was between the negative 1.58 and the positive 158, or if I go back to the exact values right here, that would be between negative square root 10 over 2 and positive square root 10 over 2. One last thing here. It did say that we could check these with the graphing calculator, and I didn't do it in the last one, but let me go ahead and check this one. If I go back to, or actually my original inequality is still sitting right here. If I go ahead and say, well, I've already got this left-hand side in as my y1, let's go ahead and put in y2 as the other side, the 15. And I'd like to graph both of these. I'm just going to start with negative 10 to 10 on both axes and see what happens. Actually, I probably should have known better than that, shouldn't I? I graphed y2 equals 15, so I know I'm going to have to go up higher on the y value. Let's go up to 20 in the y value. And what we're seeing here is that our fourth degree polynomial, this kind of a parabola-looking thing, it's not exactly a parabola, but close, right? That is less than 15, this line, between those 2 points. This part has the quartic polynomial, less than 15. On my calculator, I could get the intersection points. Oops. And there's that negative 1.58 that we had already discovered, and just by symmetry, the other one would be the positive 1.58. Calculator, of course, isn't going to give us these exact values, but we can certainly see that we get the same thing as we got when we did the decimal approximation. All right, that is the end of section 2.7.